Okay.
Okay, so sorry for technical issues that to be a bit late. I think that you enjoy some Palmiras, but meanwhile. Okay, so today we are pleased to have general seminar from our invited guest, which is Gaia Verna. She is a very young researcher. She did her master in the University of Genoa, starting with a study on CTA for searching galactic sources of cosmic rays. I also think that you got also a prize for that thesis, if I correctly remember. Yes. Then she moved to Marseille for a PhD in the University of Marseille, and also collaborating with the group in the Particle Laboratory of Marseille. I was in the name.
Centro de Partículas.
Yes, the Centro de Partículas de Marseille. She defended PhD in 2022 or 23, 22. Yes, and then we moved to Siena, where she's now a postdoc and actually coordinator of the very high energy group in Siena, together with Riccardo Folletti. So today, Gaia is gonna talk about very high energy emission from the star-forming region and also young massive star cluster. This is actually a very hot topic now in high energy astrophysics, and how to observe them, and also with and also let's say expectation from the new CTAO observatory. So back this you can start.
So first of all, sorry for the delay, and thank you for inviting me and for giving the possibility to present here. So just a little disclaimer, let's say. So my background also from my PhD thesis is a bit different. So this is part of a work that I'm doing right now in collaboration with Stefano and with the Vega group here. Yes, so I'm trying to prepare a very general introduction to the topic, pointing to the somehow the most interesting subject that on which I'm interested to. And okay, I hope you will like it. So the structure of the talk is divided in two parts. In the very first, I've tried to put the star-forming region and stellar cluster in the context of the search of the origin of galactic cosmic rays. This was the topic on which I was working also during my PhD, actually. Then I've prepared a very brief and easy introduction on how to detect gamma rays from a star cluster in general gamma rays, so on the detection technique. Speaking about space and ground-based observatory, but focusing on imaging atmospheric Cherenkov Telescope and on the future Cherenkov Telescope Array Observatory and the large-side telescope LST1. Finally, I've tried to give a brief overview on the status of the current observation with the LST1 of this type of sources, and also some challenge ahead. Okay, so first of all, star cluster are laboratory for study different kind of subject in astrophysics: stellar properties, properties of the host galaxies like size and structure, and also star formation mechanism. And here the relation with the star forming regions in the title. This is because stars usually born in cluster environments, and actually this is true in particular for massive stars. Around 80% of all type stars are observed in clusters or in association. And finally, last but not least, they are important for studying the production and the acceleration of galactic cosmic rays. And in particular, this is true in particular for young and massive star clusters. So with an age lower than 30 megayears and a mass higher than 1,000 of solar masses. So this is kind of the most interesting aspect from my point of view, and from the point of view of high energy astrophysics and gamma ray astronomy. So I have to somehow review a bit very fast the problem of the searching for the origin of the galactic cosmic rays. So first of all, cosmic rays are fully ionized nuclei. The majority of them are protons. That we can measure. Here is the cosmic ray flux measure at Earth, both with the satellites, so outside the atmosphere or on the ground. Then, okay, some general somehow description of this plot. So this flux cover 30 order of magnitude here. Oh, sorry, in flux, and over more than 10 decades in energy. So it spans really a huge huge fraction of flux and energy, and it is well described by a broken power law. With some feature, some cutoff, which somehow is an indication of an acceleration process by some cosmic ray accelerators in our galaxy or outside, so some extragalactic or galactic accelerators. We observe cosmic rays since a century, more or less, and so we have performed many measurements, not just on the flux, but also on other aspects of this flux of particles that is coming and is bombarding constantly the Earth. I put here like a list of observational constraints on galactic cosmic rays in particular. So cosmic rays that are supposed to be produced inside our galaxy, and namely the cosmic rays with energy somehow below PeV energy, below the so-called Ni feature. There is a spectral break here. And okay, here you see the list. So basically, starting from this measured flux, we have that the luminosity of the possible sources of these particles need to be of the order of 10 to the 40 ergs per second. More or less, given the spectral index of this power law, which is around the observed one, which is around minus 2.7 or 3, but giving this value of the measured spectra, we can infer somehow the spectral shape of the injected particles at the sources. And this spectra must have a spectral index of around 2.3. Another important aspect is the maximum energy of protons that we measure here. You see that the flux is divided depending on the particle that we are measuring. But for protons, the maximum energy is around 1 PeV. Then around the Ni, there is also a spectral break which depends on the atomic number. And also some other anomalies on the spectrum that we have measured with the refined measurement around the Ni somehow on protons, helium, carbon, and oxygen. Moreover, there is another one that I didn't mention, the anisotropy, for example. So we see also that the flux change depending on the latitude at which we measure the cosmic ray flux. This I didn't put here. It was not so important in the following. But yes, another important thing is the composition. So the chemical composition of the cosmic rays. We measure we see some anomalies of the measured flux of cosmic ray, the local flux, with respect to the average of the solar system. Here I put two examples. I have all the reference of the plot in the backup in case. So we measure an overabundance, for example, of lithium, beryllium, and boron, and overabundance of this isotope of neon, neon 22, with respect to the neon 20. This is another important constraint that we have to take into account in order to start thinking about what we are searching, what are the cosmic ray acceleration responsible for this particle flux. So I keep these somehow requirements here, and I want to underline the three big questions somehow on the ground. So first of all, which energy powers the acceleration of cosmic rays? So the first problem is the energy. The second one is which physics is behind the acceleration? So the physics of the acceleration mechanism. This is another question that we want to answer. And third, what is the source of the accelerated matter? So this is somehow related to the chemical composition of this sample of particles that we are measuring. So these are the big questions, and note that in general, it's not really necessary that there is just one. Maybe it could be a combination of factors that can give somehow the real answer. But somehow, since the early days, scientists have started thinking about the supernova remnant to be the main responsible of the flux of the cosmic rays, of the galactic cosmic rays. So this is so-called the supernova remnant paradigm somehow. So this hypothesis that lasted for many, many years. Let's review here the positive point of this theory. So first of all, the supernova explosion, the energy released in the supernova explosion is enough to power and supply the cosmic ray energy density that we measure. So this is a good point. We can account for the luminosity that we can somehow infer from our data. Secondly, the spatial distribution of supernova remnant are compatible with the cosmic ray distribution. This is another good point in favor of the supernova remnant hypothesis. Then the diffusion, we have somehow a strong theory, so the Fermi theory on the stochastic process of acceleration of particles that somehow is applicable to supernova remnant shock and somehow is able to explain the, in particular, the spectral index that we see here. So the power law shape of the accelerated particles, first of all, and is able also to predict the correct somehow spectral index that we get from our data. So this was a very good, a strong argument in favor of this hypothesis. And lastly, we also detect non-thermal emission from supernova remnants, in particular in gamma rays. So this somehow is the picture. But we have also some cons, let's say. So there are there is something that we cannot explain just with supernova remnant. First of all, we have no evidence of acceleration of particles beyond around 100 of TeV. So this is the first problem. We cannot explain the particle flux at around the knee, at PV energies, just with supernova remnant. And we can infer this from gamma ray observation of supernova, or shell-type supernovas, for example. We see that they have a cutoff that is not compatible with the acceleration of particle at PV. So this was a strong argument which disfavored this hypothesis. And secondly, supernova remnant cannot explain somehow the cosmic ray spectral and chemical composition anomalies that we have mentioned before. So it can this model cannot explain this paradigm cannot explain the spectral anomalies of these elements around the knee. Namely, there are some breaks at the knee for the spectra of this particle, some bumps in the spectra that we cannot explain with just somehow one source type. Secondly, also the composition. So that on the point of view of the chemical enrichment of the galactic somehow environment, supernova remnants are not enough to explain these overabundances that we measure. Okay, perfect. So we find out that we have either an incorrect or an incomplete model for supernova remnant, or we have to look for additional sources. Okay, so here starts the idea of having a possible contribution from star cluster in the flux and in the amount of cosmic that we measure. So this is somehow a meaningful hypothesis. So here is not stellar cluster, but is also supernova remnant. So it's just we are trying to add somehow in additional sources. This makes sense because if we think that the majority of supernova remnants are created from core collapse of massive stars. and the majority of massive stars explode inside the parent cluster. So there is a strong correlation between the supernova remnant and a stellar cluster, actually. This is an idea that comes pretty quite a long time ago somehow, but it was a bit not taken into account so much or till the beginning of somehow 2010. So there is really a hole in the literature, let's say. So Montmerle first proposed the possible role of OB stars, so this massing and short-lived star, in the cosmic reproduction and the acceleration. The idea was to search for gamma ray emission associated to supernova remnant in OB star association and region of ionized hydrogen. These are called like SNOBs, so these supernova remnant associated with OB clusters. And this is the paper by Montmerle. So we have here two components. We have the supernova remnants and we have the OB cluster, OB stars. So who provides the energy for the cosmic ray acceleration in these systems? But okay, it depends on the age. This is the answer somehow. So if the star cluster is young, so there are no supernova explosion yet, but in this case, the acceleration is provided only by the collective, by the wind terminator shock for just one star, or we can have also this collective wind, which is somehow the sum up of the wind terminator shock of each star of the cluster. In the other case, so if the cluster is old, but the power of is provided by the supernova remnant. So the supernova remnant are dominant in this case. Here I have somehow some sketch of the two scenarios. This is the young scenario and this is the old scenario. What happened here in the wind-driven somehow acceleration? So we have massive stars emitting a powerful winds, and these winds create these collective winds of the star cluster, okay, which is expanding. The collective wind interacts with the interstellar material and heated the gas and expands, creating a bubble-like structure, which is this one in blue, okay. This is the environment in which cosmic rays particles that obviously are inside this wind, they are particle winds, let's say, are accelerated and then are able somehow to escape and so to enrich the galactic environment of particles. Okay. Here I also given some typical scales of cluster. In this case, I'm considering a very compact cluster. Just to give you an idea on the dimension, okay? But what does it mean, a young cluster and old cluster? Here I've given some indication more quantitative, let's say. So if the age of the cluster is less than 3 MegaYears, but in this case, massive star winds drives the acceleration. On the other hand, if the cluster is older, in that case, you can see also from this plot, supernova remnant contribution to the rate of energy, somehow, here you see Earth per second, is rising and overshoot, let's say, the wind contribution, both from massive stars and then from Wolf-Rayet ray. So these are somehow a evolved state somehow of massive stars, Wolf-Rayet rays, so particular stars that are very hot and are able to produce very powerful wind. Okay, so this is Wolf-Rayet ray. Okay, so this is somehow the picture. So we want to focus, I come back here, we want to focus on this contribution, because for supernova rental, we more or less know the theory. We know that we have some limitation. So we want to focus on the contribution on the wind to the acceleration of quantum. Okay. So we want to focus to young cluster, young and massive cluster, in which we are sure that the acceleration is driven by the particle wind. So it's here. This is our interesting sample, let's say. So the ingredients for an effective cosmic ray acceleration in these systems are the following. So powerful particle winds. So we want a lot of OB stars and Wolf-Rayet ray. We want a massive and compact cluster with many stars, tens, hundreds, and in extreme cases, thousands of massive stars. Compact, so in a small volume, okay? This can boost the particle to very high energy. There are many somehow proposed models for the mechanism of acceleration of particles inside of young massive stellar cluster, and some of them are very complicated. You can have just a numerical solution to transport the equation of particles inside a turbulent environment with the magnetohydrodynamics inside. So they are very complicated because obviously you have cosmic ray acceleration, so charged particles creating also turbulence and giving feedback to the dynamic of the cluster, and so it's a very non-linear problem and can be very difficult to solve. Here I put a list of proposed model for the acceleration and propagation of in YMSC star cluster. I want just to go a bit deeper on this because actually is the one in which Stefano and Giovanni were working on, and as also the peculiarity of being somehow an analytical solution of the problem in a very somehow simplified and symmetric framework. And has the peculiarity, very nice, of being able to explain the acceleration of hadrons at PV. This for a person passionate about searching for the origin of cosmic rays is really the clue, okay? So if you are able to accelerate hadrons, that is actually the major component of the cosmic ray that we are measuring, the galactic component of the cosmic rays, but okay, you have a very interesting thing on your hands, okay? So I want just to go a little bit in detail on what happened and how things are going following this type of approach. So again, here I repeated what I said before. So we have massive stars emitting powerful wind with a collective wind of the star cluster. This wind is interacting with the interstellar medium, and the heated gas expand, creating this bubble-like structure. Following this model, what happens? So here at the termination shock, we have first order Fermi acceleration of cosmic ray at the termination shock. It's very similar to supernova remnant, actually. Okay. Then here in this region in which we have the shocked wind, we have that cosmic rays propagate within the bubble and are somehow undergo some or interact with the magnetic turbulence, so are affected by this magnetic turbulence. And so the cosmic ray diffusion, the diffusion of this particle is suppressed. It's kind of like they are confined inside this region. Finally, when the particle reach the bubble, okay, they can escape. They can eventually escape and go and propagate in the interstellar medium. Okay. So in general, the bubble-like structure is a function of the stellar cluster parameter. So it depends on the mass loss rate, on the wind luminosity, on the speed of the winds, and so on. And also on the property on the interstellar medium. Okay, so this is something important, for example, to create a model. You have a cluster, you search for this information in the literature, let's say, you try to get some information on the interstellar medium, analyzing some data, for example, for molecular clouds is radio data, and you find some parameters to put inside the model and derive, for example, the radius of the bubble or the spectral of the emission, the spectrum of the emission of the cluster. So concerning the maximum energy that the cosmic ray can reach, the spectrum and the radial distribution, these are all things that we can predict somehow with the model, given this parameter. Also, this depends on the diffusion properties. So we spoke about the diffusion here in this region, and so on the particle diffusion coefficient. We have different scenarios, and depending on the turbulence and on the injected turbulence in the shocked wind, we can have, for example, here you see a different and maximum energy of the accelerated particles. For example, you see that the bomb scenario is the more promising to have Pevatron stellar cluster, let's say. So we can reach higher energy in particles. Okay. So these three models that Stefano studied in his work differs in terms of efficiency to confine the particle inside the cluster, and more they are confined, more I can accelerate the particle at higher energy. So if the diffusion is somehow limited, is constrained, then I will have some more energetic particles coming out from after the acceleration process. Okay. Okay, so here is finished, the most theoretical part, let's say, but let's put this in the framework of the searching for the origin of galactic cosmic ray. What stellar cluster, in particular stellar cluster with supernova remnant, can give me more than the just supernova remnants, as we mentioned before. So first of all, we have that stellar cluster release the same energy of supernova remnants, and so they provide enough power to explain and to supply the cosmic ray energy density. So this somehow is unchanged. For this, we have no problems. We have this, and we can also explain we have the power law spectrum, and it's consistent with this 2.3 spectral index that we have said previously. So for this is fine. But we have also gained the possibility to accelerate particles at PV, so that was not possible with the supernova remnant alone. And also, as a bonus, we have that we can explain pretty nicely these anomalies in the overabundance of the isotope of neon. This is a really nice somehow result. So also from the point of view of the chemical composition of cosmic rays, we are satisfied. This is thanks to the Wolf-Rayleigh wind, actually, so that are really important for, and somehow they contribute more for young and massive star cluster. Okay, so after having put everything in the framework of the search for galactic cosmic rays, let's see the connection, how we study cosmic rays and how we don't study cosmic rays just directly, let's say. Actually, we have a problem with cosmic rays. Cosmic rays are charged particles, so when they propagate from their source to us, to the Earth, but they have to propagate in the intergalactic medium in which we have magnetic fields. We have magnetic fields, and then charged particles are deflected for Lorentz force, and so their path to us is randomized, and we cannot pinpoint the position of the cosmic rays source just from observing cosmic rays. Okay, so we have this issue. But the solution is to measure instead photons that are not charged particles, and so they can propagate in a more or less straight line inside the universe. So photons interacting with we want photon from matter because at the origin we have always cosmic rays. So but we want to produce photons. So apart from nuclear decays and particle decays and annihilation, we have that photons can be produced from the interaction of accelerated particles with different things, with matter, magnetic fields, or photons. In the case of a population of leptons, we have three scenarios. So we have that lepton can interact with matter, and so the emission mechanism is the Bremsstrahlung mechanism you see here. So the electron deflects inside the Coulomb field of an atom, and a photon is produced. Or we have the interaction between leptons and magnetic fields, and so we have synchrotron and also curvature radiator, synchrotron emission. Finally, if we have that leptons interact with a photon field, then we have the emission of inverse photon. This is particularly interesting, as we will see, for very energy photons, for gamma rays. In case of a population of hadrons, for example, here a proton interacting with matter, we have nuclear inelastic scattering, so PP interaction, and from the PP scattering, we have the production of the pi zero, and then the decay of the pi zero into photons, actually to gamma ray photons. Somehow on the other side, we are also producing neutrinos. We are not considering this in this stage, but they are really a smoking gun for these hadronic interactions. If we have that this proton interacts with photon fields instead, we have photoproduction. So here you see also this mechanism. Note that also the Bremsstrahlung can be important. Bremsstrahlung from protons, for example, from hadrons. It depends on the density of the medium that I'm considering. So for certain sources, it can be also efficient radiation mechanism, Bremsstrahlung from hadrons. But let's come back on gamma rays. So in considering gamma rays, very energy photons, the two most important mechanisms to produce them are the nuclear inelastic collision, so the pi zero decay, and the inverse compound. These are the two emission mechanisms. So we want to study cosmic rays, but we detect gamma rays, and we study cosmic rays and the physics of cosmic ray in an indirect way, let's say. But how we detect gamma rays? So gamma rays are too energetic, cannot be reflected by mirror or imaged by a CCD. So we cannot use a standard telescope. Since the beginning, we start using particle detectors, because at this energy, light starts showing his particle nature, let's say. So above around 1 MeV, we have that the dominant process in photon matter interaction is the pair production. Here I also show you the Compton scattering that is relevant for energy below 1 MeV, more or less. Note that the pair production cross-section depends on the square of the atomic number. So if we want to efficiently detect gamma ray, efficiently absorb this energy, we need high material with a high atomic number. So first idea is to use satellite. So we go outside the atmosphere and we can build a pair conversion telescope, such as the most important one, Fermi-LAT, at the moment, let's say. So these type of telescopes are efficiently detecting high energy gamma rays in the range of hundreds of MeV to hundreds of GeV, even higher. They have a photo collection area of around 1 meter square, an angular resolution of around 0.15 degrees, and a large field of view, 3 steradiant, so 24% of the sky. Okay, but they are not enough for very energy gamma rays. So they are fine till GeV, but then it is not enough. So let's do a little exercise. Let's see that is not enough. Okay, let's consider, for example, the brightest gamma ray source, the Crab Nebula, and let's consider the count rate from this source in gamma rays at energy above 1 TeV. So we have around 10 to the minus 17 photons per second, which means more or less a photon every few months. What is telling us? It's telling us that this rate is too low. So if we want to detect photons a bit faster, we need a collection area which is a bit larger than 1 meter square. Okay. If we take a typical power law, because usually gamma ray sources somehow emit light photons following a power law spectrum, we take an index -2. But we see that the flux decreases by 6 orders of magnitudes if we pass from 1 GeV to 1 TeV. What does it mean? But it doesn't mean that beyond 100 GeV, we need at least 100,000 bigger collection area. And for this reason, we cannot stay outside the atmosphere. We have to go down on Earth. So the interaction between a gamma ray with the molecules of the atmosphere creates showers of charged particles, which propagates inside the atmosphere at a velocity which is higher than the light velocity inside the atmosphere itself. So these showers emit Cherenkov light that we can detect with the imaging atmospheric Cherenkov telescope here at a bit lower altitude. Another way to detect these showers and to reconstruct the gamma ray at the origin is also to sample directly the extensive eye shower of particles using some water tanks, so some particle detector arrays that are usually at higher altitude, around 3,000 meters above the sea level. Okay, and again, exploit the production of the Cherenkov light, this time produced by charged particle, passing through the water inside the water tanks that can be, and this light, the Cherenkov light, can be detected at PNTs on the base of the tanks. Okay, these are two different methods. We will focus in the following. We will see briefly the differences between the detection method, but we will focus on the imaging atmospheric Cherenkov telescope. I want also to underline that, okay, these flash of Cherenkov light, they are really short in time, tens of nanoseconds. So we need very fast electronics, very fast cameras made of photomultiplier to detect them. Moreover, we can think about an array of this kind of Cherenkov telescope in order to reconstruct better somehow the original gamma ray by imaging this very same shower from this different perspective and then constrain better the arrival point on the ground, which is related to the arrival point on the atmosphere, so the direction of the shower actually. To constrain better also the energy of the initial particles and its nature. Because actually, also cosmic rays interacting with the atmosphere create showers of particles, and so Cherenkov light. And then we need a way to distinguish between hadronic and electromagnetic showers. Okay, so I put here an overview on the somehow performance of these two techniques. So for the YMSCs, the energy range at the moment goes between hundreds of GeV till 30 TeV, even higher in particular observational condition, let's say, or with particular observational configurations. We have a low duty cycle in general, down to 15%, and a modest field of view, around 4 degrees with the current generation of telescopes. The angular resolution, on the other side, is pretty well. It goes down to 0.08 degrees, which is better with respect of the one that particle detector array can reach. So they have worse angular resolution, but on the other hand, they can reach higher energy. They can go even beyond 1 PV, thanks to the huge collection area. So basically, these water tanks are really cheap. You can cover a huge area basically for free. It's really easy to build somehow. And so they can exploit this potentiality to measure gamma rays up to PV energies. They have also another big advantage. So they have a nearly 100% duty cycle. They can observe in every time, okay, even during the day and during the night. This is not true for Cherenkov telescope, because this faint, the Cherenkov light is can be detected efficiently just in dark night, and so the duty cycle for this reason decreases. They have also a large field of view, and so they are particularly suitable for studying extended sources. Okay, let's go to the future generation of Cherenkov telescope. So the Cherenkov Telescope Array Observatory. It is an international project that will have the peculiarity of being the very first observatory. Here I didn't mention, but we have 3 telescope arrays in operation today. So HES, Veritas, and Magic. They are all 3 telescope arrays. And they are instruments, they are experiments. So just people inside the collaboration can use the data and produce the scientific results. Gamma ray, Cherenkov Telescope Observatory, CTA, wants to be different. So it will be an observatory, so any scientist will have the possibility to submit a proposal and to analyze the own data. Okay. The overall performance of CTAO will be from a factor 5 to 10 better in sensitivity with respect to the current generator of ICTs. And this will be true over a wider energy range from 20 GeV up to 300 of TeV. So it's very big. This is not possible just with one telescope type, let's say. So to reach these requirements, these goals, the idea has been to have a compromise between sensitivity, performance, and cost of the telescope, and having 3 types of Cherenkov telescope: the large-sized telescope, the medium-sized telescope, and the small-sized telescope. Okay, each one is optimized for a different energy range. In particular, LST is optimized for the lower energy, so in the transition between high energy, let's say, and very energy. look at the improvement in terms of energy range with respect to the current generation. CTAO will be deployed on 2 sites, so this telescope will be put on 2 different arrays, one in the Northern Hemisphere, CTAO-North, and one in the Southern Hemisphere. So the Southern array will be in the Atacama Desert, and it will be composed by 15 telescopes, 14 MSTs, and 37 SSTs. The Northern array will be in La Palma, close to the MAGIC telescope, actually, and it will be composed by 4 LST and 9 MSTs, covering a smaller area, so 0.5 kilometers square for the Northern array and 5 kilometers square from the Southern array. So you can imagine that we spoke about collection area. So the Southern array will have a better sensitivity at high energy when the flux of gamma rays is lower, and will be optimized then for the study of very energy sources. Concerning the CTA-North, so I'm focusing on this array now because it's basically under construction. So we have the first LST here, which has been inaugurated in 2018 and is currently under commissioning. What does it mean? But it means that the priority now is given to the technical operation, to the calibration, to the optimization of the, and also to the, we want to reach somehow the requirement fixed by CTAO to be accepted officially as a CTAO telescope. So this is the priority now for the LST collaboration. But then part of the time, since few years, is also devoted to science. And for example, last year, they were allocated around 500 hours of observation time for science proposals. At the moment, due to the fact that MAGIC telescope, there are 2 telescopes of around 17 meters, the mirror, the primary mirror is 17 meters. But okay, they are close by to LST at a distance which is lower than 100 meters, which is somehow the size of the Cherenkov pool. So basically, with the system of LST and the 2 MAGIC, it is possible to see in coincidence the very same shower, and so to operate as a small array of 3 telescopes. This since the few years is possible, so part of the observation are also as a joint observation with MAGIC. And this, the fact of observing with additional telescope means an improvement in terms of the sensitivity of around a factor 1.5 with respect to LST alone, so it's very important. Here I give also some few characteristics of LST in terms of energy coverage, camera, focal length, and so on. So I pass here to the somehow to sum up. So let's come back on star cluster. I want to give you here an overview on the ongoing project in LST related to star cluster. The first one has been a proposal that me, Stefano, Javier, and so on submitted last year, and it is on the star cluster NGC 6611 in the Eagle Nebula, the famous pillars of creation. Probably you remember the beautiful picture by Hubble. And okay, it has the characteristic of being a young and massive star cluster, which is visible at the LST site at medium zenith angles, so around 43 degrees above the horizon. Here are the parameters of the stellar cluster. It is interesting because for the very first time last year, our collaborator Giada Peron were able to detect Fermi emission from this cluster. This emission is point-like, so it is smaller than the angular resolution of Fermi, so 0.2 degrees GeV. And the best fitted, here you see here in the plot, fitted spectral model is a power law. You can see here. Stefano kindly produced the expected spectral emission from the famous model that I've described before, so the one with the termination shock, the collective termination shock, in two different scenarios in terms of turbulence. You remember, Bohm and Cracknell. So the Bohm was the one more optimistic in terms of maximum energy of the accelerated particles. As you can see, somehow the produced gamma rays are also going toward higher energy. Okay, so that was connected. So particles are more confined, so they can accelerate till higher energy, and so also the gamma ray produced can they have a cutoff at higher energy. Okay. So we also somehow here in the plot we try also to evaluate, okay, the possibility of detecting this source at very energy was never detected before, so we thought it is worth trying. In particular, it is interesting for LST because the emission that we see is at GeV, so we want to be on the transition of the Fermi band and the very energy band. So here you see the sensitivity curve, so the minimal flux that LST can detect at 5 sigma in 50 hours of observation. And we also put as comparison the sensitivity curves of the 4 LST. So as I said, we have just one LST, but the other 3 will be built soon, and of the full CTAO-Northern array. So with an LST, it seems challenging. Probably if we will get some hours, additional hours, because we get just 2 hours, more or 3 hours of observation, so not so much. But we will be able to maybe put some limits on the emission of the star cluster. But as you can see, with the LST array and with the full northern array, it becomes an interesting target, let's say. So we asked for 50 hours of observation. Yes, and I also want to mention that this cluster is a bit close to the galactic plane. This challenge is close to the galactic plane and close to some bright stars that with a particular observational pointing we are trying to avoid. But okay. It will be challenging, the analysis. I will also show you the sky map just to have an idea. So here you see the dust, the emission from the dust, cold and hot, of the galactic plane. Here's the position of NGC 6611, so M16, so the source that we are pointing. Here the two bright Hess sources close to the galactic plane. And here with the W2 and W1, I show you the pointing of LST that we have chosen somehow. As you can see, we are trying to point our telescope a bit higher in order to avoid as much as possible the galactic plane, which give us some somehow additional background due to the gamma ray emission from the dust of the galaxy. And you can also see, if you are not maybe in the field, that the strategy for standard observation is to do some pointings at a slightly offset from the position of the source. So we are not pointing directly to our source, but with a small offset. In our case, we choose 0.5 degrees offset, okay, in this direction. This is a standard way to observe the very energy sources with EICTs, due to the fact that later in the later stage of the analysis, when we want to extract the signal from the source region, we are trying to somehow calibrate our background, which is intrinsically present also in the region in which we think that there is a gamma ray source. But we try to normalize the background, taking some the counts somehow measured in the outer part of the field of view, okay, in the hypothesis that the response of the instrument is radially symmetric, and so that the number of count at a fixed offset from the camera center is somehow predictable, easily predictable, let's say. So this is a standard way to observe the source. I want here to pass to the second stellar cluster, second and last stellar cluster that we are considering, which is a very famous one, probably the most famous in the Northern Hemisphere, which is the Cygnus cocoon. So this is a OB cluster, a B association in reality, is one of the most massive star cluster in the galaxy. And it has the best visibility in the Northern Hemisphere. So this is very important. We can see the Cygnus just from the northern side, from MAGIC, from LST. Okay, so it's not visible on the other hemisphere. So it's a perfect target for the Northern Array. So first of all, I want to present these results that are more related to the model before. So some results on the modeling of the emission of the source. I was describing this termination shock, acceleration of the termination shock. I want to show just here that with some data, Stefano and collaborators have tried to fit with this with the model produced in this very somehow ideal hypothesis and with a analytical resolution of the equation, let's say. So it's a very like test cases, but a very simple one. But okay, you can see that you can actually fit pretty well the observed data in the hypothesis of hadronic population of particles. So what we see is gamma ray emission from accelerated protons, and in particular from accelerated proton at very high energy and even ultra high energy, because this cluster has been detected also by particle detector arrays that I've introduced before, which are able to were able to detect the very first photon at PV energy exactly from the Cygnus cocoon. Okay, so from the point of view of observation, is a challenging source because it's very extended, both in the Fermi energy range and in the LASO ones. And so for YMSCs that, as I was mentioned before, they have a limited field of view, it's a challenging sources. What we are trying to do also with LST is to try to reconstruct the emission of the region using a new, different observational technique. I was speaking about the different pointing at a fixed offset from the source. In this case, we are trying to perform a drift scan of the region, meaning that the telescope is like standing in a constant position in alt azimuth, so it's like fixed toward pointed in the sky. It's not tracking the source, let's say, and the sky drifts in front of it and in the camera, let's say. And what you can do is like trying to map even extended the region and try to overcome the problem of the limited field of view, let's say. So to try to exploit as much as possible the limited field of view, even for mapping a very extended region. This is, let's say, the second time that we are trying to do this in this field, let's say. There was already an attempt, but as far as I know, was not successful. The results in this case are promising, let's say, but we still need to a bit evaluate on the technical point of view the technique and to validate it. So another thing that we are trying to do with the group is to somehow submit a technical proposal on evaluating this new observational technique, not on a very complicated cluster, but on our standard candle in embedded energy, which is the Crab Nebula. Okay, so perform a drift scan of our standard candle. Coming to the conclusions, I've presented somehow the connection between the star cluster and in particular the young massive stellar cluster with the big question about the origin of galactic cosmic rays. So star cluster and in particular young ones are powerful cosmic ray acceleration and also gamma ray emitters. I've cited an example of a high energy emitter star cluster, so M16, that we are trying to observe also with LST. And this could be an interesting target because its emission could be at the border between the Fermi and the LST energy range. And I also cited the Cygno cocoon example, which is another type of cluster, very extended, with a lot of mass, a lot of clouds, with the emission which is detected up to very energy and ultra energy in gamma rays, and which is one of the best Pevatron candidates that we have for sure in the Northern Hemisphere, let's say. Then I try to say that the theory also behind for describing the emission of stellar cluster is complicated, and starting from the data, we need the robust modeling of the, from the modeling part, we need robust modeling for describing the cosmic ray propagation in the neighbor of these sources. And also from the data, instead, a detailed spectra and morphological study in the gamma ray band. So this is a joint effort that must be done on the phenomenological, theoretical side and the experimental one. Finally, in collaboration with the Very Energy Group here, we are working on several tasks. So first, on the submission of a new proposal for the upcoming cycle, this time with MAGIC and LST, try to improve the sensitivity and put some more constraining upper limit, maybe on the emission of M16. And also on a technical proposal for the validation of the LST drift scan of the Crab Nebula. Moreover, we are also thinking about future observation of the subarray of 4LST and also of the future CTAO-Northern array. Try to ranking the best stellar cluster to be observed from CTAO-Northern. Okay, thank you for the attention.
Thank you, Gaia. So we have questions or comments? Yes, please.
Thank you for this. I thought about gamma ray, cosmic rays, and zero-drum emission. Regarding the zero-drum emission, I want to mention that we have detected no thermal radiations in around projected by intermediate mass protostar with only 2 solar mass. Perhaps you can also search for cosmic ray sources or gamma ray sources in intermediate mass, not only in young massive stellar cluster. Indeed, in young stellar, in this cluster, there are intermediate, low mass star and massive star all live together. And my question here is, how do you know if the sources, the gamma or cosmic sources, are indeed mass star? It could be intermediate mass star, not indeed, but perhaps you don't have the angular resolution to identify them, no?
No, that is not possible actually. And what you see from the cluster is like the collective emission of all the stars. You cannot really distinguish one by one, let's say. And it's also hard to somehow mapping the star population of the cluster. Also in the literature, it's hard sometimes to find, so you have big uncertainty on the number of stars in the cluster, on the age. So I think that, for example, the mass is related to this initial mass function that you have in the. This is something difficult to estimate. Is very difficult. So we cannot really have an idea. We have a total mass of the cluster, let's say, an idea of. How many, for example, OB stars there are in the clusters, because maybe they are surveyed, we know that. And so we can estimate how many massive stars there are there, I would say. But then you cannot distinguish the emission from the single star or you have somehow overall emission.
I only want to emphasize that we have detected no thermal emission associated with intermediate mass protostar. We only do solar mass. No?
You say the synchrotron in any case, right?
Yes, it could be synchrotron.
Okay.
Right now, as far as I know, Marco Padovani is studying this source in Orion. We know in Orion there exists a protostar of different luminosities, but in this case, it was only intermediate mass producing no thermal emission, and perhaps it is a sort of cosmic ray.
Yes, the fact is that, okay, for synchrotron, I expect electronic population as a main contributor to the emission. And in the context of the search for the origin of galactic cosmic ray is not what we are interested in. So we really want to point to the hadronic emitters. Because, I mean, if we come back to the famous cosmic ray flux, local flux, yes, you see that yeah, the protons are the dominant one. So if we are interested to this. Also, when I speak about Pevatron, I mean if I am attached to this scientific question to hadronic Pevatron. So
maybe I can also add a comment about this. So that what Marco is working on is actually isolated young medium stellar objects. Here we are talking about also clusters with many OB stars. And the power by the wind of the OB stars are much larger with respect to young stars forming. The point is that if you have a very large power, which some of it is dissipated in turbulence from the winds, you have a rising up in the magnetic field, which kills completely, or you are expecting to kill completely electrons. So you can have synchronous emission, but in order to explain like very high energy emission, in that case is a bit tricky because the electron will probably be completely killed by radiation losses, which is not the case in isolated young stellar object.
In started that I have already mentioned is not isolated.
It's in clusters?
Yes.
Okay, okay, I didn't know that. Okay. Okay, that was like isolated young stellar object. Okay.
It's very crowded.
Okay, okay.
Sorry.
No. So I think that we have an online question. Also, you, Paula, you raise your hand, please.
Okay.
Yes. And then
So my question is more or less on this line, but it's more general. I mean, I know that it's not strictly connect the synchrotron emission with what we are looking for. But maybe I don't know, I'm just adding this a question, if the radio observation can give us at least some information about the environment and about how is, I don't know, magnetic field, and if it can help somehow to know how is the diffusion there in this.
yes, so the point is we want to distinguish electronic and hadronic radiation and gamma rays, which is challenging.
Of course. Yeah.
For sure, with the radio observation, we can see the emission from molecular clouds. And if we see a spatial correlation between our gamma ray emission and the molecular clouds, this strongly favors the hadronic scenario. So this is the standard argument in which we are trying to do. So with better and better angular resolution, we try to constrain as much as possible these possible spatial coincidence and try to point to the to hadronic sources. For sure, knowing the synchrotron emission is important also because the synchrotron emission can be the photon field for the inverse Compton emission. So if we know better the synchrotron emission, we also can predict better. So they are basically connected. It is called the synchrotron self-component. No? So, I mean, they are connected, the two, the emission of the synchrotron emission and the inverse Compton emission can be connected. So there is a population of electrons accelerated producing synchrotron and electron scattering of the very same synchrotron emission, the photon field, produce inverse Compton. So if you can constrain better the synchrotron emission, you can also predict better the contribution at high energy of the inverse Compton. So.
But also you cannot how is the magnetic field?
Yes, exactly. So this.
Okay, we
Next
have
slide. Next slide.
we have a question from online. I don't know if yeah, he need to open the microphone. I don't know if you can hear us, Jose.
Yeah.
Yeah.
Well, thank you for the nice talk. It's a very, very interesting subject, and the talk was very good. I have just a small question. I think you have mentioned before the role of Wolf-Rayet stars. So my question is whether because you are saying you are pointing OB clusters. My question is related to the role of Wolf-Rayet stars in this cluster, whether they are actually an important amount of the whole budget, or even if individual Wolf-Rayet stars in the galaxy can be targeted and detected or not. Thank you.
Okay, so for sure we are trying to search for the clusters with as much Wolf-Rayet stars as possible, let's say. This is interesting for different reasons, in my opinion. So here you see that they give here a contribution, a wind contribution at around 3 megayear, let's say. That can be interesting to study because they contribute to the acceleration of particles as well. They're giving also somehow a kick to the cosmic rays. So they also play a role here. And I also mentioned before that they are interesting for the chemical composition of
yeah, the neon anomaly.
So for sure we are trying. I think that I don't know if there are some surveys or some like a database in which they are how can I say mapped in the clusters. Exactly, that's the point. As far as I remember, it's always a big uncertainty how many Wolf-Rayet there are in the clusters, and it's not very easy somehow to.
Yeah. Okay, but then
maybe you can have an estimation of how much you have in the cluster and make some different scenarios and see how change the emission considering more or less Wolf-Rayet.
Is it impossible to target one single massive Wolf-Rayet star by nowadays, or is it still too faint? Or
I don't know.
So maybe I can answer. In principle, yes, you can target single Wolf-Rayet. The point is that you have very large wind power. So in principle, you would expect a very fast wind. So in principle, you can have strong shocks where you can accelerate particles. The point is that whenever you want to go for observing gamma ray emission, well, that is can be a problem, because in clusters where you have many Wolf-Rayet in general, you are surrounded by a lot of gas, which is required to make hadronic gamma ray emission. While single Wolf-Rayet stars, they have powerful wind, they can eject a lot of mass, but this mass is not as much, or at least enough, to get, let's say, an appreciable hadronic gamma ray emission. But still, you can have electrons also acceleration, and then maybe you can look for leptonic emission. So in principle you can, but I don't know if currently there are estimation over that.
Okay, very interesting. Thank you very much.
You're welcome. There is also another hand raised, yes.
I have raised my hand, but I don't know if it's my turn.
Yeah, please.
Okay. Thank you very much from the talk. I learned a lot. I just wanted to know you can give us a scales of how much is the time scale of the duration of these bubbles of gamma rays that form in clusters at the first ages when the winds are collective and
So
producing.
here, more or less,
Let me just finish. It's just because I wonder. I think the power is enormous. It looks to me, but I don't know exactly. You say a number about 10 to the 40. I don't know if sum up is this number what we expect, but this is amount of energy which is injected in the medium around, and eventually might even quench star formation in other regions, in other molecular clouds around. So I go in that direction. I want to know how long do they last, and the scale, size, and time, in size and time.
Yes, let's say I would say that this is the interesting plot, right? So you have the different contribution to this energy from the winds, the Wolf array, so from the stars basically, and then for the supernova. That at a certain point they take over and they dominate this energy. This is the kinetic luminosity. So basically is as far as I know is the energy that is somehow provided to cosmic rays during the acceleration.
Oh, that one actually is the total injected energy. So
But
the one that in principle goes into inflating the bubble.
But this is total transfer. So as much as I have in winds, as much I have in cosmic rays?
No. In general, that one, the plot that is showing is the power from wind and also supernovae. And then a fraction of it, in general 1 to 10%, is in cosmic ray.
Is the efficiency. Yes, it's true. That is the same of the supernova.
Yes.
So
And so how long is expected to last this bubble? Well, I suppose it might depend on metal. I don't know. How long is it?
Well, maybe I can answer to this. So it is not that clear in the sense that, so in terms of size, because you also asked size, in general, you have bubbles around tenths up to 100 in the most powerful cases, parsecs. For how long does it last? Well, it really depends, because in general, you have that the evolution of a super bubble is divided in two phases. The first one is the free expansion, where you have that the shocked gas freely expand in the interstellar medium, and also you have an adiabatic expansion. At some point, you start to expand, you start to cool, and then you have the onset of radiative cooling, which basically start to decelerate the expansion of the bubble. But at this point, also, once you start the deceleration and you have the onset of radiative cooling, the gas start to cool and start to collapse. And if you have, like, for example, this shell of expanding material, those shells will start to fragmentate, creating also new molecular clouds. And at some point there, you cannot anymore, let's say, talk about a bubble. You basically are triggering actually star formation, and you have the creation of molecular clouds. So this, how much does it take? Well, it's a good question. By heart, I would say 10 or 10-ish of mega years.
Yeah.
For sure, radiation losses start to kick in at around 10 mega year, more or less, 7 to 10 mega year. That is more or less the age. Then it really depends on also on the configuration of where you're expanding. So case by case can really change, but the order of magnitude is somewhere around that.
Yeah. I found that this could be a lot of energy, and I'm thinking more in extragalactic systems, or where you have a lot of star formations. There's much more of this cosmic rays produced, and if all this is released out in the medium, in the stellar medium, even if you are 100% or even larger, you might stop star formation in other clouds. I see a difficulty to enhance star formation by producing clouds by that, because this is a lot of energy put in the medium. So you go against gravity for collapsing.
Yes, but you also trigger it by inducing collapsing, no? Now I'm not an expert on feedback, so I must admit that I have some limitation from that side, but you of course you can have both positive and negative feedback at some point, because you can sweep away the gas, but at some point if you cool it and you make it collapse, you will also creating new molecular clouds and then trigger star formation. So I guess that also really depends on how many of these systems you have around. I'm thinking about like starburst regions, when you actually have starburst galaxies, when you have many of these objects and you can actually create galactic wind, and also you have ejection of gas outside the galaxy.
Yeah, but that time scale as well, no? Because if it takes 10 million years, it means that I sort of quench star formation for a given period, and then because of the collapse, you say, cooling of the medium, you can trigger again star formation. That depends on the time scale, among other things. Okay, thank you very much. Very interesting.
Thank you for the comment. So I guess that there are no other questions. We can thank again Gaia. And thanks for everyone for having attended the seminar. Thank you.